Definition of context-free grammar and its theorem. In this video, we are going to see about definition of context-free grammar and its theorem. A context-free grammar, that is CFG, consisting of a finite set of grammar rules is a quadruple, that is N, T, P, S, where N is a set of non-terminal symbols. T is a set of terminals where N intersection T is equal to null. P is a set of rules. P, N provides N union T, the whole power asterisk, that is, the left-hand side of the production rules P does have any right context or left context. S is the start symbol. Example: the grammar A, ABC, P, A, P, A provides small a, capital A, capital A provides small a, small b, small c. The grammar S, A, B, A, B, P, S, P, S provides A, S, A, S provides B, S, B, S provides epsilon. The grammar S, F, 0, 1, P, S, P, S provides 0, S or 11F, F provides 0, F or epsilon. There are two different approaches to draw a derivation tree: top-down approach, bottom-up approach. Top-down approach starts with the starting symbol S, goes down to tree leaves using productions. Bottom-up approach starts from tree leaves, proceeds upward to the root, which is the starting symbol S. Derivation or yield of a tree. The derivation or the yield of a parse tree is a final string obtained by concatenating the labels of the leaves of the tree from the left to right, ignoring the nulls. However, if all the leaves are null, derivation is null. Example: let a CFG N, T, P, S be N is equal to S, T is equal to A, B, starting symbol is equal to S, P is equal to S, provides SS or ASB or epsilon. One derivation from the above CFG is AB, AA, BB. S provides SS, provides ASBS, provides ABS, provides ABASB, provides ABAASBB, provides ABAABB. Leftmost and rightmost derivation of a string. Leftmost derivation. A leftmost derivation is obtained by applying production to the leftmost variable in each step. Rightmost derivation. A rightmost derivation is obtained by applying production to the rightmost variable in each step. Example: let any set of production rules in a CFG are over an alphabet A, X provides x plus x or x into x or x or a. The leftmost derivation for the string a plus a into a may be x provides x plus x provides a plus x provides a plus x into x provides a plus a into x provides a plus a into a. The rightmost derivation for the above string a plus a into a may be x provides x into x provides x into a provides x plus x into a provides x plus a into a provides a plus a into a. Left and right recursive grammars. In a context-free grammar, G, if there is a production in the form x provides xa, where x is a non-terminal and a is a string of terminals, it is called a left recursive production. The grammar having a left recursive production is called a left recursive grammar. And if in a context-free grammar, G, if there is a production is in the form x provides ax, where x is a non-terminal and a is a string of terminals, it is called a right recursive production. The grammar having a right recursive production is called a right recursive grammar. Properties of unions, concatenations, and cleans of context-free language. In this video, we are going to see about properties of unions, concatenations, and cleans of context-free language. Closure properties of CFL. The context-free languages are closed under some operation means after performing that particular operation on those CFLs, the resultant language is context-free language. These properties are as below. The context-free languages are closed under union. The context-free languages are closed under concatenation. The context-free languages are closed under clean closure. The context-free languages are not closed under intersection. The context-free languages are not closed under complement. Theorem 1. If L1 and L2 are context-free languages, then L is equal to L1 union L2 is also context-free. That is, the CFLs are closed under union. Proof. We will consider two languages, L1 and L2, which are context-free languages. We can give these languages using context-free grammars G1 and G2 such that G1 element of L1 and G2 element of L2. The G1 can be given as G1 is equal to V1, summation, P1, S1, where P1 can be given as P1 is equal to S1 provides A1, S1, A1 or B1, S, B1 or epsilon. A1 provides A, B1 provides B. Here, V1 is equal to S1, A1, B1 and S1 is a symbol. Similarly, we can write G2 is equal to V2, summation, P2, S2. N2 is equal to S2, A2, B2 and S2 is a start symbol. P2 can be given as P2 is equal to S2 provides A, capital A2 or B, capital B2, capital B2. A2 provides B, B2 provides A. Now, L is equal to L1 union L2 gives G epsilon L. This G can be written as G is equal to V, summation, P, S. V is equal to S1, A1, B1, S2, A2, B2. P is equal to P1 union P2. P is equal to S provides S1 or S2. S1 provides A1, S1, A1 or B1, S, B1 or epsilon. Capital A1 provides small a. Capital B1 provides small b. S2 provides A, capital A2 or B, capital B2, capital B2. A2 provides B, B2 provides A. Thus, grammar G is a context-free grammar which produces languages L, which is context-free language. Theorem 2. If L1 and L2 are two context-free languages, then L1, L2 is CFG. That means context-free languages are closed under concatenation. Proof. Let L1 is a context-free language which can be represented by a context-free grammar G1 such that G1 epsilon L1 and G1 is equal to V1, summation, P1, S1. V1 is equal to S1, A1, B1. Summation is equal to A, B. S1 is a start symbol and P1 is a set of production rules. P1 is equal to S1 provides A1, S1, A1 or B1, S1, B1 or epsilon. Capital A1 provides small a. Capital B1 provides small b. Similarly, is a context-free language which can be represented by a context-free grammar G2 such that G2 epsilon L2 and G2 is equal to V2, summation, P2, S2. V2 is equal to S2, A2, B2. Summation is equal to A, B. S2 is a start symbol and P2 is a set of production rules. P2 is equal to S2 provides small a, capital A2 or small b, capital B2, capital B2. A2 provides B, B2 provides A. Now, L is equal to L1, L2 can be obtained by G such that G is equal to G1 into G2. Therefore, G is equal to V, summation, P, S. V is equal to S, S1, A1, B1, S2, A2, B2, where S is a start symbol. The production rules P can be given as P is equal to S provides S1 or S2. S1 provides A1, S1, A1, A1 or B1, S1, B1 or epsilon. A1 provides A, capital B1 provides small b, S2 provides small a, capital A2 or B, capital B2, capital B2. A2 provides B, B2 provides A. As grammar G is context-free grammar, the language L produced by G is also context-free language. Hence, context-free languages are closed under concatenation. Theorem 3. If L1 is context-free language, then L into 1 is also context-free. That means CFL is closed under clean closure. Proof. Let L1 be a context-free languages represented by G1 such that G1 provides epsilon L1. The CFG G1 can be given as G1 is equal to V1, summation, P1, S1, where S1 is a start symbol. P1 is equal to S1 provides A1, S1, A1 or B1, S1, B1 or epsilon. Capital A1 provides small a, capital B1 provides small b. Now L is equal to L into 1 can be represented by a grammar G such that G is equal to V, summation, P, S. V is equal to S, S1, A1, B1 and P is equal to S provides S1, S or epsilon. S1 provides A1, S1, A1 or B1, S1, B1. Capital A1 provides small a, capital B1 provides small b. Thus, grammar G is a context-free grammar and a language L produced by G is also context-free language. Hence, context-free language is closed under clean closure. Definition of derivations and languages. In this video, we are going to see about definition of derivations and languages. The production rules are used to derive certain strings. We will now formally define the language generated by grammar G is equal to V, T, P, S. The generation of language using specific rules is derivation. Definition. Let G is equal to V, T, P, S be the context-free grammar if A provides beta is a production of P, alpha and gamma are strings from non-terminals or terminal, that is V union T to the power of asterisk, then small a capital A provides small a, beta, gamma. Suppose A1, A2, A3 up to AM are strings in V union T to the power of asterisk M greater than or equal to 1. A1 implies A2, A2 implies A3 up to A, M minus 1 implies AM. Then we can say that the language generated by G is denoted by L of G. The language L is called context-free language, CFL, if L of G is for CFG. For example, G is equal to S, B, A, B, S provides small a, capital B, small b, S. B provides B, B, B is a grammar. Then we can derive a string A, B, B, B as we will first start from start symbol S. S implies small a, capital B, small b. Then we will replace capital B by small b, small b, small b. S implies small a, capital B, small b implies small a, small b, small b, small b. Thus, we can obtain the desired language L by certain rules. The language L can be described as a language which starts with letter A and having 4 B's following. Theorem for relationship between derivation and derivation trees. In this video, we are going to see about theorem for relationship between derivation and derivation trees. Theorem. Let G is equal to V, T, P, S be a context-free grammar. Then S implies A if there is a derivation tree in grammar G which gives the string A. Proof. If there is a non-terminal S in V, then S implies A if and only if there is a S tree which gives the string A. We can easily prove this using induction theorem. We can apply induction on number of interior nodes. Basis of induction. Let us assume S is the only one interior which gives a string A which can be obtained by deriving S provides A1, A2, A3 up to AN. Then there exists a derivation tree which derives A1, A2, A3 up to AN and gives the string A. Induction step. We assume that the derivation will enable us to draw the tree with k-1 interior nodes. We have to prove that it is possible to draw the derivation tree for k interior nodes which gives the string A. In the derivation tree, not all the nodes are leaves or interior nodes. Some are leaves whereas others are interior nodes, considering for them S is a parent node. Thus, this derivation tree will ultimately give the string N. Leftmost derivation and rightmost derivation. As we know, derivation for any string means replacement of non-terminal by its appropriate definition. There may be a situation in which there are many non-terminals. Then, which non-terminal should be replaced by its definition is sometimes confusing to decide. Hence, we normally apply two methods of deriving. The leftmost derivation is a derivation in which the leftmost non-terminal is replaced first from the sentential form. The rightmost derivation is the derivation in which rightmost non-terminal is replaced first from the sentential form. Let us see how it works. For example, S provides XYX. S provides XYX. S provides AYX. S provides XYA. S provides ABX. S provides XBA. S provides ABA. S provides ABA. Leftmost derivation, rightmost derivation. Note that we have replaced first X from left or right in leftmost derivation and XYX, the last X, that is the rightmost symbol. Actually, we may use a leftmost derivation or rightmost derivation. We get the same string. The type of derivation does not affect on getting of a string. Problem on leftmost and rightmost derivations. Example: derive the string AA BB A BBA for leftmost derivation and rightmost derivation using a CFG given by S provides AB or BA. A provides A or AS or BAA. B provides B or BS or ABB. Solution. Let us see the leftmost derivation first. S AB. S provides AB. AABB. B provides ABB. AA, small b, capital B provides small b. AA, BB, S, B, capital B provides small b, S. AA, small b, A, capital B, S provides AB. AA, BB, AB, S, capital B provides small b, S. Small a, small b, small b, capital A, S provides BA. AA, BB, A, BB, A, capital A provides small a. Now, let us solve using rightmost derivation. S. AB, S provides AB. AA, BB, B provides ABB. AA, capital B, small b, S, capital B provides small b, S. Small a, capital B, capital A, capital B provides small b, capital A. Small a, capital B, small a, capital A provides small a. AAB, S, BBA, capital B provides small b, S. Small a, small b, capital A, small b, small a. S provides small b, capital A. AA, BB, A, BB, A, capital A provides small a. Ambiguity and its problem. In this video, we are going to see about ambiguity and its problem. If a context-free grammar G has more than one derivation tree for some string W element of L of G, it is called an ambiguous grammar. There exist multiple rightmost or leftmost derivations for some string generated from that grammar. Problem. Check whether the grammar G with production rules is ambiguous or not. Solution. Let's find out the derivation tree for the string a plus a into a. It has two leftmost derivations. Derivation 1. X provides x plus x provides a plus x provides a plus x into x provides a plus a into x provides a plus a into a. Parse tree 1. Derivation 2. X provides x into x provides x plus x into x provides a plus x into x provides a plus a into x provides a plus a into a. Parse tree 2. As there are two parse trees for a single string a plus a into a, the grammar G is ambiguous. Unambiguous CFG and algebraic expressions, its theorem. In this video, we are going to see about unambiguous CFG and algebraic expressions, its theorem. Although it is possible to prove that some context-free languages are inherently ambiguous in the sense that they can be produced only by ambiguous grammars, ambiguity is normally a property of the grammar rather than the language. If a CFG is ambiguous, it is often possible and usually desirable to find an equivalent unambiguous CFG. The grammar that we end up with is G1 is equal to V, summation, S, P, where V is equal to S, T, F, and P contains the production. S provides S plus T or T. T provides T into F or F. F provides of S or A. We must now prove two things. First, that G1 is indeed equivalent to the original grammar G, and second, that it is unambiguous. To avoid confusion, we relabel the start symbol in G1. Theorem. Let G be the context-free grammar with productions. S provide S plus S or S into S or of S or A. And let G1 be the context-free grammar with productions. S1 provides S1 plus T or T. T provides T into F or F. F provides of S1 or A. Then L of G is equal to L of G1. Proof. First, to show L of G1 subset of L of G. The proof is by induction on the length of a string in L of G1. The basic step is to show that A element of L of G, and this is clear. In the induction step, we assume that K greater than or equal to 1 and that every Y in L of G1 is satisfying. Modulus of Y lesser than or equal to K is in L of G. We must show that X element of L of G1 and modulus of X is equal to K plus 1, then X element of L of G. Since X not equal to A, any derivation of X in G1 must begin in one of these three ways. S1 implies S1 plus T. S1 implies T into F. S1 implies T implies F implies S1. We give a proof in the first case and the other two are very similar. If X has a derivation beginning S1 implies S1 plus T, then X is equal to Y plus Z, where S1 implies into G1 into Y and T implies G1 into Z. Therefore, since modulus of Y and modulus of Z must be lesser than K, the induction hypothesis implies that Y and Z are both in L of G. Since G contains the production S provides S plus S, the string Y plus Z is derivable from S in G and therefore X element of L of G. Second, to show L of G subset of G1. Again, we use induction on modulus of X, and just as in the first part, the basic step is straightforward. We assume that K greater than or equal to 1 and that for every Y element of L of G with modulus of Y lesser than or equal to K, Y element of L of G1, we wish to show that if X element of L of G and modulus of x is equal to k plus 1, then x element of L of G1. The simplest case in which x has a derivation in G beginning S provides of S. In this case, x is equal to y for some y in L of G, and it follows from the induction hypothesis that y element of L of G1. Therefore, we can derive x in G1 by starting the derivation S1 implies T implies F implies of S1 and then deriving y from S1. Suppose x has a derivation in G that begins S provides S plus S. Then just as before, the induction hypothesis tells us that x is equal to y plus z, where y and z are both in L of G1. Now, however, in order to conclude that x element of L of G1, we need z to be derivable from T. In other words, we would like z to be a single term, the last of the terms whose sum is x. With this in mind, let x is equal to x1 plus x2 plus up to plus xn, where each xi element of L of G1 and n is as large as possible. We have already determined that n greater than or equal to 2 because of the way n is defined. None of the xi's can have a derivation in G1 that begins S1 implies S1 plus T. Therefore, every xi can be derived from T in G1. Let y is equal to x1 plus x2 up to plus xn minus 1. Z is equal to xn. Then y can be derived from S1 since S1 implies asterisk G1 T plus up to plus T n minus 1 term, and Z can be derived from T. It follows that x element of L of G1, since we can start with the production S1 provides S1 S plus T. Finally, suppose that every derivation of x in G begins S implies S into S. Then for some y and z in L of G, x is equal to y asterisk. This time we let x is equal to x1 asterisk x2 asterisk up to asterisk xn, where each xi element of L of G and n is as large as possible. Note the difference between this statement and the one in the previous case. Then by the inductive hypothesis, each xi element of L of G1, what we would like this time is for each xi to be derivable from F in G1. We can easily rule out the case where some xi has a derivation in G1 that begins S1 implies T asterisk F. If this were true, xi would be of the form yi asterisk zi for some yi comma zi element of L of G1. Since we know L of G1 subset of L of G, this would contradict the maximal property of the number n. Suppose that some xi had a derivation in G1 beginning S1 implies S1 plus T. Then xi is equal to yi plus zi for some yi comma zi element of L of G1 subset of L of G. In this case, x is equal to x1 asterisk x2 asterisk up to xi minus 1 asterisk yi plus zi asterisk xi plus 1 asterisk up to asterisk xn. This is impossible too if we let u and v be the substrings before and after the plus respectively. we clearly have u, v element of L of g, and therefore x is equal to u plus v. This means that we could derive x in g using a derivation that begins s implies s plus s, and we have assumed that this is not the case. We may conclude that each xi is derivable from f in g1, then as we did in the previous case, we let y is equal to x1 asterisk x2 asterisk up to asterisk xn minus 1, z is equal to xn. The string y is derivable from t in g1, since f asterisk up to asterisk f of n minus 1 factors is. Therefore, we may derive x from s1 in g1 by starting the derivation. S1 implies t asterisk f, and so x element of L of g1. In order to show that grammar g1 is unambiguous, it will be helpful to concentrate on the parenthesis in a string, temporarily ignoring the other terminal symbols. Definition: balanced strings of parentheses. A string of left and right parentheses is balanced if it has equal numbers of left and right parentheses and no prefix has more right than left. The mate of a let parenthesis in a balanced string is the first right parenthesis following it, for which the string containing those two and everything in between is balanced. If x is a string containing parenthesis and other symbol, and the parenthesis with x form a balanced string, a symbol sigma in x is within parenthesis if sigma appears between some left parenthesis and its mate. The first observation we make is that the string of parentheses in any string obtained from S1 in the grammar G1 is balanced. Certainly, it has equal numbers of left and right parentheses since they are produced in pairs. Concept of Backus-Naur form, that is BNF. In this video, we are going to see about concept of Backus-Naur form, that is BNF. BNF is one of the earliest forms of notation used for describing the syntax of a programming language. Backus-Naur form, that is BNF. This is basically just a variant of a context-free grammar, with the symbol equal to used in place of provides to mean is defined as. Additionally, non-terminals are usually written in angle brackets and terminals in quotes. For example, we could describe a block of statements in Pascal as block equal to begin, that is opt statements, end. Opt statements equal to statements list or epsilon. Statements list equal to statement or statement semicolon statements list. An extension of this notation known as extended BNF, that is EBNF, allows us to use regular expression like constructs on the right hand side of the rules. For any sequence of symbols alpha, we write alpha in angular bracket to say that alpha is optional, and alpha in set bracket to denote 0 or more repetitions of alpha, that is, the clean closure of alpha. Thus, we could rewrite the above rules in EBNF as block double colon equal to begin, that is statements list, end. Statements list double colon equal to statement, statement. We could describe the complete syntax of a programming language using EBNF or equivalently a CFG, but it tends to make things easier if we break it up into two sections. The lexical syntax, which defines which patterns of characters make up which words. This can be described using regular expressions. The context-free syntax, which defines which sequences of words which make up phrases from the programming language. We describe this using a context-free grammar. Thus, the first task in writing a parser for a language is breaking up its syntax into the regular and context-free part. The choice is arbitrary, but a simple guideline is that characters from the input should not appear in the context-free syntax. These should be tokenized by the lexical phase. As well as modularizing our task, this approach will facilitate debugging in parser generators such as YACC. CNF, that is Chomsky normal form. In this video, we are going to see about CNF, that is Chomsky normal form. A CFG is in Chomsky normal form if the productions are in the forms: capital A provides small a, capital A provides BC, S provides epsilon, where A, B and C are non-terminals and A is terminal. Algorithm to convert into Chomsky normal form. Step 1. If the start symbol S occurs on some right side, create a new start symbol S dash and a new production S dash provides S. Step 2. Remove null productions, that is, using the null production removal algorithm. Step 3. Remove unit productions, that is, using the unit production removal algorithm. Step 4. Replace each production A provides B1 up to Bn, where n is greater than 2, with A provides B1C, where C provides B2 up to Bn. Repeat this step for all productions having 2 or more symbols in the right side. Step 5. If the right side of any production is in the form capital A provides small ab, where A is the terminal and AB are non-terminal, then the production is replaced by A provides XB and X provides small a. Repeat this step for every production which is in the form capital A provides small ab. Problem: convert the following CFG into CNF. S provides ASA or small a capital B, capital A provides capital B or S, capital B provides small b or epsilon. Solution: since S appears in RHS, we add a new state S0, and S0 provides S is added to the production set and it becomes S0 provides S, S provides ASA or small a capital B, A provides B or S, capital B provides small b or epsilon. Now we will remove the null productions. B provides epsilon and A provides epsilon. After removing B provides epsilon, the production set becomes S naught provides S provides ASA or small a capital B or small a provides B or S or epsilon, capital B provides small b. After removing A provides epsilon, the production set becomes S naught provides S provides ASA or small a capital B or small a or capital A capital S or capital S capital A or capital S. A provides B or S, capital B provides small b. Now we will remove the unit productions. After removing S provides S, the production set becomes S naught provides S provides ASA or small a capital B or small a or capital A capital S or capital S capital A provides B or S, capital B provides small b. After removing S naught provides S, the production set becomes S naught provides ASA or small a capital B or small a or capital A capital S or capital S capital A. S provides ASA or small a capital B or small a or capital A capital S or capital S capital A. A provides B or S, capital B provides small b. After removing A provides B, the production set becomes S naught provides ASA or small a capital B or small a or capital A capital S or capital S capital A. S provides capital A capital S capital A or small a capital B or small a or capital A capital S or capital S capital A. A provides S or small b. Capital B provides small b. After removing A provides S, the production set becomes S naught provides ASA or small a capital B or small a or capital A capital S or capital S capital A. S provides capital A capital S capital A or small a capital B or small a or capital A capital S or capital S capital A. Capital A provides small b or capital A capital S capital A or small a capital B or small a or capital A capital S or capital S capital A. Capital B provides small b. Now we will find out more than two variables in the RHS. Here S naught provides ASA, S provides ASA, A provides ASA violates two non-terminals in RHS. Hence, we apply step 4 and step 5 to get the following final production set, which is in CNF. S naught provides AX or small a capital B or small a or capital AS or capital SA. S provides AX or small a capital B or small a or capital A capital S or capital S capital A. Capital A provides small b or capital A capital X or small a capital B or small a capital S or capital S capital A. Capital B provides small b. Capital X provides capital S capital A. We have to change the productions. S naught provide small a capital B. S provides small a capital B. Capital A provides small a capital B. And the final projection set becomes S naught provides capital A capital X or capital Y capital B or small a or capital A capital S or capital S capital A. S provides capital A capital X or capital Y capital B or small a or capital A capital S or capital S capital A. A provides B or capital A capital X or capital Y capital B or small a or capital A capital S or capital S capital A. Capital B provides small b. Capital X provides capital S capital A. Capital Y provides small a. Deterministic PDA and its example. In this video, we are going to see about deterministic PDA and its example. The push-down automata, that is PDA, is essentially a finite automation with control of both an input tape and a stack, or last in first out, that is LIFO list. The symbols can be entered or removed only on top of the storage stack. When a symbol is added on top, the symbol previously on top becomes a second, and so on. Similarly, when a symbol is removed from the top of stack, the symbol previously second from the top becomes top symbol, and so on. The languages which can be recognized by PDA are precisely the context-free languages. Definition of push-down automation. A push-down automation P is equal to Q, summation, gamma, delta, Q naught, Z naught, F is given by the following data. A finite set Q of states. A finite set summation of symbols, that is the alphabet. A finite set gamma of stacked symbols. A transition function. Delta element of Q into summation union of element of into gamma provides P base of fin into Q into gamma to the power of asterisk. Here, P base fin of A are the finite subsets of a set, that is, this can be defined as P base fin of A is equal to X, or X subset of A intersection of X is finite. An initial state Q naught element of Q. An initial stack symbol Z naught element of gamma. A set of final states F subset of Q. PDA state diagram. Example. Consider the language LWWR is equal to WW to the power R, or W is in 0 plus 1 to the power of asterisk. Solution. The design of push-down automaton to accept the language is as follows. Language is palindrome over alphabet 0, 1. Start in a state Q naught, read symbols till the end of the string W and store them on the stack by pushing a copy of each input symbol onto stack. We guess we have seen the middle, so go to state Q1. Once in Q1, we compare input symbols with the symbol at the top of the stack. If they match, we consume the input symbol, pop the stack and proceed. If they do not match, then input string is not palindrome. If we empty the stack, we have seen input W followed by W to the power R. The string is accepted. PDA P of Q, summation, gamma, delta, Q naught, Z naught, phi. Q is equal to Q naught, Q1, Q2 is equal to number of states. Summation is equal to 0, 1 is equal to input symbol alphabet. Gamma is equal to 0, 1, Z naught. Start state is equal to Q naught. Start stack symbol is equal to Z naught. Final state is equal to Q2. Delta is initial state of the PDA. Set to push W onto stack. Delta of Q naught, 0, Z naught is equal to Q naught, 0 Z naught. Delta of Q naught, 1, Z naught is equal to Q naught, 1 Z naught. First symbol push on stack. Delta of Q naught, 0, 0 is equal to Q naught, 0, 0. Delta of Q naught, 0, 1 is equal to Q naught, 0, 1. Delta of Q naught, 1, 0 is equal to Q naught, 1, 0. Delta of Q naught, 1, 1 is equal to Q naught, 1, 1. Grow the stack by pushing new symbols on top of old, that is W part. To find middle of the string, NPDA switches state from Q0 to Q1. Delta of Q0, epsilon, Z0 is equal to Q1, Z0. Delta of Q0, epsilon, 0 is equal to Q1, 0. Delta of Q0, epsilon, 1 is equal to Q1, 1. Switch to popping mode, non-deterministically, boundary between W and WR. Match WR against contents of stack. Delta of Q1, 0, 0 is equal to Q1, epsilon. Delta of Q1, 1, 1 is equal to Q1, epsilon. Shrink the stack by popping matching symbols, that is WR part. To reach final state, delta of Q1, epsilon, Z0 is equal to Q2, Z0. Enter acceptance state. To reach final state, delta of Q1, epsilon, Z0 is equal to Q2, Z0. PDA for LWWR transition diagram. The languages of a PDA. Acceptance by final state. Let M is equal to Q, summation, gamma, delta, Q0, Z0, F be a PDA. Then the language accepted by M is a set of strings such that L of M is equal to W or Q0, W, Z0, or minus to the power of asterisk P, epsilon, Y. P element of F, Y element of gamma to the power of asterisk. That is PDA M, consumes W from the input and enters an accepting state. Acceptance by empty state. Let n of m be the language accepted by m is given by theorem for equivalence of CFG and PDA. In this video, we are going to see about theorem for equivalence of CFG and PDA. A language is generated by a CFG if and only if it is accepted by a PDA by empty stack. If and only if it is accepted by a PDA by final state. From CFGs to PDAs. Theorem. For any context-free language L, there exists an PDA M such that L is equal to L of M. Proof. Let G is equal to V, T, P, S be a grammar. There exists a grayback normal form. Then we can construct PDA which simulates leftmost derivations in this grammar. M is equal to Q, summation, gamma, delta, Q naught, Z, F, where Q is equal to Q naught, Q1, Qf is equal to set of states. Summation is equal to terminals of grammar G. Gamma is equal to V union of Z, where V is the variables in grammar G. F is equal to Qf is equal to final state. The transition function will include delta of Q naught, lambda, Z is equal to Q1, Sz, so that after the first move of M, the stack contains the start symbol S of the derivation. The stack symbol Z is a marker to allow us to detect the end of the derivation. In addition, the set of transition rules is such that delta of Q1, lambda, A is equal to Q, alpha for each capital A provides alpha in P. Delta of Q, A is equal to Q, lambda for each A element of summation. From PDAs to CFGs. Theorem. If L is n of m for some PDA m, then L is CFL. Proof. It has a single final state Qf if the stack is empty. All transitions must have the form delta of Qi, small a, capital A is equal to C1, C2 up to Cn, where delta of Qi, small a, capital A is equal to Qj, lambda provides 1. Delta of Qi, small a, capital A is equal to Qj, capital B, capital C provides 2. That is, each move either increases or decreases the stack content by a single symbol. Given m is equal to Q, summation, gamma, delta, Q naught, Z naught, Qf satisfies the condition 1 and 2. G is equal to V, T, P, S. V elements of the form, that is Q, A, P, Q and P in Q and A in gamma. T is equal to summation. S start symbol. S provides Q naught, Z naught, Q for each small q in capital Q. P consists of U, V element of summation to the power of asterisk. a comma x element of gamma to the power of asterisk qi comma qj element of q qi comma uv comma ax minus to the power of asterisk minus qj comma v comma x implies that qi comma a comma qj provides u. Consider qi comma a comma qk provides small a, q is equal to j, b comma ql, ql comma c comma qk. The corresponding transition for PDA is delta of qi comma small a comma capital A is equal to qj comma bc goes on. Similarly, if qi comma a comma qj provides a, then the corresponding transition is delta of qi comma small a comma capital A is equal to qj comma lambda. For all sentential forms leading to a terminal string, the argument holds true. The conclusion is q0, w, z0 minus to the power of asterisk minus of qf, lambda is true if of q0, z0, qf implies to the power asterisk w or consequently L of m is equal to L of g. Context-free language, that is CFL, and its example. In this video, we are going to see about context-free language, that is CFL, and its example. Context-free language, that is CFL, and its example. We defined the right linear grammars by giving a simple restriction on the form of each production. By relaxing that restriction a bit, we get a broader class of grammars, the context-free grammars. These grammars generate the context-free languages, which include all the regular languages along with many that are not regular. Example: we can prove that these languages are not regular, yet they have grammars. A to the power of n, b to the power of n. S provides small a, capital S, small b, or epsilon. X to the power of r or x element of a comma b to the power of asterisk. S provides small a, capital S, small a, or small b, capital S, small b, or epsilon. A to the power of n, b to the power of j, a to the power of n, or n greater than or equal to 0, j greater than or equal to 1. S provides small a or capital S, small a, or r. R provides small b, capital R, or small b. Although not right linear, these grammars still follow a rather restricted form. A context-free language, that is CFL, is one that is L of g for some CFG g. Every regular language is a CFL. Every regular language has a right linear grammar. Every right linear grammar is a CFG. But not every CFL is regular. A to the power n, b to the power n. X to the power of r or x element of a comma b to the power of asterisk. A to the power n, b to the power j, a to the power n, or n greater than or equal to 0, comma j greater than or equal to 1. Balanced pairs. CFLs often seem to involve balanced pairs. A n, b n. Every a paired with b on the other side. X to the power of r, or x element of a comma b to the power of asterisk. Each symbol in x paired with its mirror image in x to the power r. A to the power n, b to the power j, a to the power n, or n greater than or equal to 0, j greater than or equal to 1. Each a on the left paired with one of the right. To get matching pairs, use a recursive production of the form r provides x to the power r y. This generates any number of x's, each of which is matched with a y on the other side. Pumping lemma for CFL and its proofs. In this video, we are going to see about pumping lemma for CFL and its proofs. The pumping lemma for regular sets states that every sufficiently long string in a regular set contains a short substring that can be pumped. In other words, if a long string is given and if we push or pump any number of substrings any number of times, we always get a regular set. According to pumping lemma for CFLs, there are always two short substrings that are close to each other, and these substrings can be repeated as many times as required. Lemma. Let L be any context-free language. Then there is a constant n, which depends only upon L, such that there exists a string z element of L and modulus of z greater than n, where z is equal to uv wxy, such that modulus of Vx greater than or equal to 1, modulus of Vwx lesser than or equal to NAND, for all I greater than or equal to 0, uv to the power of I, wx to the power of I, y is in L. Proof. This pumping lemma states that in a language L, that is without unit productions and without productions, there exists a z where z element of L. The string z can be derived by a context-free grammar G. Let G be a grammar and let it be in the Chomsky normal form. For the string z, we can obtain a parse tree that derives the string z. The depth of the path from root to the leaf node for the yield z is less than or equal to I. Then length of the word z is less than or equal to 2i minus j. We can prove this by induction. Basis: if I is equal to 1, let G contains the rules S to 7a, where length of the derived string is 1, that is I is equal to 1. Now according to the rule, the word length should be lesser than 2i minus j is equal to 2 power 0 is equal to 1. Observe that we have a word which is of length 1. Also observe that the grammar G is in Chomsky's normal form. Hence, the language is regular since modulus of z is equal to modulus of uv wxy is equal to 1. Induction step. Let w be a string that is derived by grammar G. Let k be a variable such that n is equal to 2k and modulus of z is greater than n. Then modulus of z greater than 2k minus j. When deriving the string w, we may get some non-terminals of CFG. G to be repeated any number of times to give the string Z as shown in the figure. If we pump the substrings to W such that the path length of its newly formed string Z dash, that is Z plus pumped string Z dash is I, and the word length of Z dash is 2 I minus j, then the grammar G deriving Z dash is called a regular grammar. The necessary condition is that grammar G is in Chomsky's normal form. Let us consider the following grammar. G is equal to A, B, C, A, A to 7BC, or A, B up to 7BA, or B, C up to 7BA, A. Thus, A implies to the power of asterisk small b a is equal to W, that is length I is equal to 3. Modulus of W lesser than or equal to 2 to the power of I is equal to 1, comma, that is 3 lesser than or equal to 2 to the power of 2. If we pump substrings into W which satisfies the condition I lesser than or equal to modulus of W lesser than or equal to 2I minus T lesser than or equal to N, then the grammar producing the string W is a regular grammar.